Assalamualaikum and good morning. My name is AIMAN MAZIZ bin MUSTATAFA and I am from Group 9. And my job is to explain the project's problem. Our group has chosen option B, which is the robot maze navigation. This would involve an autonomous robot that must find the shortest path from the starting point into the goal point in a 6x7 warehouse grid. There are 4 types of cell. The empty cell, which the robot can move into, the block cell and the shelf cell, which the robot cannot move into, and the goal cell, which would be the endpoint of the robot. Now, the robot can only do an up, down, left, and right movement, and would only be valid if the grid boundary is inside and not into an obstacle. Now, our team has done a zero-index Python implementation to make it easier for us to locate it. As we can see, the initial state starts at 50, and the goal state starts at 06. Now, there are 42 states within this grid, and operator would need to use an up, down, left, right, which would cost them at least 1 point. Now, the algorithm that we have used for this project is the BFS algorithm, the DFS algorithm, the greedy best first search algorithm, and the A-star search algorithm. Now, onto the state space representation, which is the search tree. As we can see, the blue node is the root node, which is the initial state at 50. Each edge and branching would mean that the operators are being applied. The red node represents the dead ends or obstacles. The dashed line that we can see there are paths that lead to obstacle cells and are pruned to prevent any infinite loops or reduce the search space. The yellow node would mean that we are moving smoothly towards the end goal. And as we can see, the green node is at 06, which means that we can find the node at the most fastest pace.
Assalamualaikum and salam sejahtera. My name is Muhammad SYAKIR from FARID and I'm responsible for the part 3. Group 9. I use Python to code 4 different ways the robot can navigate the warehouse. Okay, as you can see, this is our maze grid. It consists of 6x7 grid, and S is start, G is goal. Okay, for the next part is def by the positions. This loop scans the grid to identify the start and the goal coordinate. Okay, next one is our heuristic. It calculates the distance to the goal using the Manhattan formula. Basically, counting the square the robot must move. Okay, next is BFS. It uses Q. It explores level by level, making sure it finds the shortest path possible. Okay, now for the second one, it is DFS. It uses stack. It explores as deep as it can in one direction before it backtracking. Okay, now for the third part is the greedy set. This is a set that remembers where the robot has already been, so it doesn't walk in circle. Okay, now for the next part. As you can see, I use a priority queue here. This automatically keeps the best looking path at the top for the robot to try first. Okay, next is F score equal to new G heuristic. This is the logic we add the step already taken G to the estimate distance left H. This balance helps the robot reach the goal quickly and optimally. Last but not least, this is the help queue and help push. This line saves our new path back into the queue ranked by its total cost. Okay, now as you can see, this is our output. Although A expanded fewer nodes than BFS, SYAKIR's execution time is slightly higher due to the additional overhead computing Fn equal to Gn plus Hn, and maintaining the G-score dictionary for each code on a larger grid. This overhead become negligible as the node of reduction in advantage compounds significantly. That's all from me. Thank you, everyone.
My name is SIDRATULMUNTAHA and my matching number 078334. I will present the part for heuristic. So what is heuristic and why Manhattan distance? We can use a straight line distance here because the robot cannot cut through walls diagonally. Manhattan distance counts the actual number of row and column steps needed, which matches exactly how our robot moves. And so this is the mathematical formula for the Manhattan distance and the Python code below it. For example, on the grid, if the robot is here at 41 and the goal is at 06, the Manhattan distance estimates 9 steps remaining. The actual path may be longer due to the obstacles, but it will never be shorter, which is exactly what we need. Is our heuristic valid? Admissibility is important because it guarantees A star will always find the optimal path. Our heuristic is safe. Shelves and block cells can only force the robot to take the longer route. So our estimate is only equal to or less than the real cost. For the impact on performance, both Grady and A star use the Manhattan distance heuristic. However, we compare BFS and A star here specifically because both guarantee the optimal path, which is 11 steps, making it fair comparison of efficiency. BFS had no guidance, so it blindly expanded 30 knots. A star used Manhattan distance to focus only on the promising directions, cutting that down to 20 knots, a 33% improvement, while still finding the exact same optimal 11-step path. Now that we have seen how the heuristic works, let's move on to the full performance comparison where we evaluate all 4 algorithms together.
Salam Sejahtera, my name is ATHAVAN and I would like to explain the performance comparison for our project Robot Maze Navigation within a maze environment. First of all, we use these 4 algorithms to help us decide which algorithm can help the robot to navigate the maze efficiently without wasting too much computational resources. So we have 2 informed algorithms, and 2 uninformed algorithms, and 2 informed algorithms: BFS, DFS, greedy search, and A search. Uninformed, uninformed algorithm means that uh, it's not notified on the starting node and the final coordinates, which is the delivery goal. So basically, it just brute forces its way through. Meanwhile, greedy search and e-search employs a Manhattan heuristic to help them navigate between the starting coordinate and the final delivery coordinate. When using the Manhattan distance, since the robot can only move up, down, left, and right, basically it helps us to calculate the total distance navigated by the robot itself. So in order to prevent these 4 algorithms from looping in and in themselves, we use a visited set optimization to prevent this 4 algorithm from navigating the same paths that they had taken previously, so that we can optimize the memory usage. So I would like to explain the time and space complexity. Basically, breadth first search guaranteed the 11 step optimality, and yet it expended so much memory by going through 30 steps, which is highly inefficient, and it expends so much memory queue by navigating 71% of the 6 times 7 grid. Next is DFS, which is the worst overall. Not only is it expanded 27 nodes, but it took a whole 17 steps to navigate the warehouse, since it had to go through dead ends in the warehouse and is forced to backtrack. Next is the informed algorithm. As you can see with greedy search, it optimally obtained the 13 part step while expanding 18 nodes, and yet this is considered inefficient because it basically just circle around the same place, circle around the same obstacle. So it's also inefficient at the end of the day, despite achieve the 13th step. It's obvious the winner here is the A search algorithm, which only expanded 20 nodes and achieved the optimal 11 step, demonstrating efficiency and optimality.